So this whole presentation is really about practically how did we go about porting our engine that was very glass focused into Vulkan. And of course we made a lot of compromises, and this is just one way of doing it. There are many, many ways to port something to Vulkan, but this is in practice how we did it. So here's sort of the rough outline. We're going to cover how we dealt with command buffers, pipelines, all these things. But first, this is, if you can condense everything from today into one slide, maybe this is a good slide. Almost all the work done in the driver is now the engine writer's job, which makes things much more complicated. And we have to think about a lot more things. We can't just assume that the driver will do everything for us. We do everything ourselves now, almost everything. So, a lot of things in Vulkan. Just to get something on screen, you have to master all these things, and probably a couple more. There are the memory heaps, we have to manage them in a sensible way. We have descriptor pools to create descriptor sets. We have to create all these handles, bind them correctly into a command buffer, submit, all these things, just to get something on screen. But this has been covered today quite well already, so I'm not going to go into detail about that. So the first thing you have to think about is that, sure, old graphics engines tended to rely on GL and D3D in that everything just happens for you automatically. You just write some layer that lets you create a texture, lets you draw stuff, and you have a very thin layer over the API basically. But that won't really work anymore, because we found that if you try to take that kind of API and try to make it work in Vulkan, it's not going to work. Or you have to make some extreme performance sacrifices, which why would you port to Vulkan anyways? So we found out you should approach it from a different angle. Try to design or redesign your interface for Vulkan and make that work in GL or some other API. That's much easier in practice. So the first thing we have to deal with, obviously, is memory. So in GL, we don't really care about that because we create textures, we create buffers. It's allocated for us, and the driver will handle it. It may page out stuff, do bad things performance-wise, but it should work. But in Vulkan, we have to write our own memory allocator from scratch. So we need them to decide that. So allocating memory in Vulkan is very expensive. We can't do that. We're not going to create a texture and then allocate memory with VK allocate commands. We really need to allocate huge blocks and manage those blocks ourselves. That's the only way to get good performance in this case. Another thing we have to think about is that there's no ref counting in the drivers. We have to manage the lifetime as well. And it's not just the CPU, it's also the GPU. So before we reclaim memory or destroy it, we need a way to make sure that nothing is using this memory. The way we deal with this is a simple block-based memory allocator. So in our memory manager, the only thing it cares about are large chunks of memory. Let's say 2 or 4 megabytes at a time. So the only things that are allocated and reclaimed are these big blocks. Every time we make an allocation, it allocates a chunk of that and adds a ref count to that block. When everything that uses that block is freed, it could potentially be reclaimed. But we also have to make sure that all uses on the CPU are over due to ref count. That's fine, but we also need to make sure that the GPU has completed all its work. So it's sort of a defer thing. Ref count is 0, actually defer the reclaim until the GPU is done. And to deal with this sort of deferring thing, we actually use the swap chain indices for this, which was mentioned in Tobias's talk with like how to make things overlap. If we have 3 frames in our swap chain, what we end up doing is we start with a block in the first frame. When we start a new frame, we terminate the current block, start a new block, allocate from that, and keep going. And when we get back to the first frame again, the swap chain, the GPU should pretty much always be done with that frame, because it's like 2-3 frames old. And at that time, we wait for a few fences to make sure that, okay, GPU is definitely done. We can now reclaim the first one. And at that point, we never allocate again. After a certain amount of time, the memory manager has always blocks available for any kind of streaming. That's fairly simple to implement as well. Command buffers. So earlier we had to decide, do we want to try reusing command buffers or not? And if we start with reuse, obviously it could have gains, but it's also very difficult. So what we ended up with, if we can assume that we will never reuse anything, this makes allocation very simple, because an application will just request a command buffer, record it, submit, and forget about it, which means that managing this becomes very simple, because the application never owns anything. It just borrows the command buffer for the sake of recording it. So to have overlap and multi-threading, we essentially allocate a command pool per worker thread, or also the main thread, per swap chain index, so that we can overlap between frames, and separate pools for primary and secondary command buffers, so that, if we want to allocate a secondary command buffer, we allocate that from the secondary pool and the primary comes from the primary pool, and stuff like that. And this means that at the start of every frame, when we wait for a semaphore, or we wait for a fence, we simply reset all command pools and reuse all command buffers, so we never reallocate command buffers again. That works out pretty well. This would be way more complicated to reuse, but that could have other benefits, but we didn't really go into that. How we use secondary command buffers, we use them quite extensively, since we can't really assume how big a render pass would be. So what we end up doing is that every large render pass we state up front, is this a multi-threaded thing or a single-threaded thing? If it's a multi-threaded thing, we end up splitting up our work into secondary command buffers and execute that in the main thread afterwards. Ideally, we would be able to pipeline multiple passes this way, but we haven't. We did go into that. That's a very straightforward way of how to get multi-threading done. And of course, all these threads, like threads 0, 1, and 2, come from separate command pools. These are just handled automatically, because every worker thread knows its ID. It will just, I need a command buffer, I will go to that pool, grab a command buffer, done. Very straightforward. The next problem we had to solve was, how do we do shaders? We used to have this pretty unmaintainable system with text-based mangling to get stuff into GLSL, ESSL, some old code paths that with EX, which we just discarded, we weren't using it anymore. But it was basically unmaintainable. And if you're not a compiler person, that's what you end up doing, right? You write some crazy text replacement system to do the shaders. But this wasn't sustainable after all. So this is how the Spurvy Cross project got started. We needed some way to deal with Vulkan and GL at the same time without going crazy. This is what we ended up with. We found out we could actually just write everything in OpenGL cell and just make it work in GL. And also, we didn't want to write pipeline layouts all the time and write, like sort of state all this pipeline information up front. We wanted this to be done automatically. And that's also stuff we added down to make it work. So how we dealt with pipelines then? So in GL, things are very simple. We just set a bunch of state and it just works. Although it might trigger some driver recompilation or shader recompilations here and there, but overall it's a very simple model. And ideally, we would create all the pipelines up front, right? Ideally, we should know that we're going to use all the shaders in these render states, and we'll just create all the pipelines like that. But it is pretty complicated. There is a lot of state that goes in there, and especially for a large project or a large semi-large application, it's very annoying to have to know from every single thing you ever do. So our approach then is to have a simple state interface and simply have some kind of hash function to get the pipeline. And this hash function should be done very fast. It should be, in basically all cases, you will have a pipeline in that cache, and you will describe that and then render. And only check the hash map if state has changed and so on. That's a very straightforward way of doing it. It's probably not the most optimal, but it's a very practical way to do it. So, with the combinations thing, so one of our shaders, this is like a generic fragment shader that can support everything, has over 9,000 combinations, potentially. There's no way you're going to know up front exactly which ones you're using. So consider if-def alpha test, if-def normal map, if-def all these things. If you start to add the combinatorics, it's actually over 1 million, but you can prune some statically at least. Some of combinations don't make sense. Like you're not going to have alpha testing if you're not going to have a texture or something like that. So, but still, there are just too many combinations. Fortunately, though, we are creating a lot of pipelines, but we have the pipeline cache. And the pipeline cache can be serialized to disk, which is a very cool feature, because even though we are creating a lot of pipelines, at least we don't have to recompile shaders every time, because they're already in the pipeline cache on disk. So it's only the first time we load the application that this is an actual problem. And in theory, you could send this over the internet. Like the first time, you could like ship the pipeline cache over the internet on the first time your application starts. That stuff is actually possible. So it means that ideally you never compile a shader on the application side. That's how we end up doing that. Pipeline layouts, again, as you can imagine, Spurry Cross was the solution here. But we need to figure all of these things out. And we don't really try to use a very sort of master pipeline layout for everything. It's certainly possible, but for our purpose it wasn't very practical. So what we end up doing is that every shader just creates a pipeline layout, and that's about it. And if they happen to be the same, then that's cool, we can reuse that. Descriptor sets is also a thing that could be done better, in that ideally you would know all the things up front. You know all your materials, you would know everything. But in practice, that would make the API very tedious to use, because we'd have to, for every single object, try to bake everything. It gets very annoying, unless you redesign your engine completely from scratch to do this. So what we ended up instead is like, sure, we just set textures, set stuff, have some hash map, to have pre-created descriptor sets. And in practice, it means that after a few frames, you always find your descriptor set in the cache, and you never actually build descriptor sets. You just reuse something that has been used before. It really comes down to how fast can you do these invalidations and checking stuff. Turns out to be pretty okay for our purpose at least. Maybe if you're doing 100,000 draw calls and changing stuff all the time, this is probably not the best solution. But for a regular application, I think this is more than adequate. Of course, descriptor pools and stuff are just handled automatically. So if we try to create a descriptor set, we don't just create a pool with one descriptor set. We pool it up into, let's say, 16 descriptor sets at a time to amortize the allocation costs. But again, we still need to support this thing less, because our engine should support less as well. So how do we do this? Well, again, Spurry Cross lets us just fiddle around with the bindings, and we can create some mapping function. So let's say that our shader splits textures and buffers up into multiple sets there. We can sort of allocate per type into a new thing where we have uniform buffer binding from 0 to 2 here, and texture bindings from 0, 1, 2. And that mapping is trivial, because it turns out you can just set 2, get some offset, plus binding gives you the real binding. Very simple, straightforward approach, worked out quite nicely. Of course, this wouldn't deal with like bizarre cases where you have a binding at 40 here, because that would create a binding error for you, but just don't do that. I mean, you control what the shader should be doing. Don't try to make it difficult for yourself. Push constants is especially important for the knowledge GPUs and some other GPUs certainly, but we really care about this because they are effectively register mapped and you can avoid certain, you don't have to load from a uniform buffer because it's preloaded for you, basically. But if we want to support push constants, how do we make this work? We have to make this work in class as well. So what we ended up with is our main interface will have some way of saying update constant registers with this blob of data. In Vulkan, that translates directly to EKC and the push constants, very straightforward and simple. But in GL, essentially, we can translate this to a series of GL uniform calls automatically. So the GLs behind the scenes will look at, this is our current shader. Okay, I will just loop through this list of function pointers and that turned out to be okay. Maybe not the best way to do it, but it's practical. Render process is very good. So this was a great refactoring opportunity for us as well, because we had a GL style interface which didn't deal with render process, but now we had the opportunity to do it properly. So your interfaces need to, if you want to support, let's say, GL and Vulkan, it really needs to have a concept of a render class in the interface. That's the only way to make it sensible. So, but there are other things that are pretty tedious, like defining a render class or defining the multi-pass stuff. So what we end up doing is that we say, we have a render class, we're going to write to these textures, maybe we're going to write to some virtual things, like transient allocated textures, just say, but I don't really care about the storage, just give me some shallow gbuffer space for my deferred pipeline. And we end up internally checking, do we have this, have we seen this framebuffer before, and that kind of stuff. Just again, simple hashing style way of doing it. We request the render class, we create the render class if we haven't seen it, we create the framebuffer, but in the common case we have seen everything and we have the render class and then we just begin. That's a problem if you change the texture every time, but why would you do that? Because the sort chain especially has everything allocated up front, because you know exactly where you're rendering all the time. So for subpass inputs, this is also, we had pretty decent pixel local storage support, obviously, because we care about these things. So we needed a way to make this work in both Vulkan and GL at the same time. So we ended up extending our render pass to also add multipass information, which is where the virtual attachments came in. We say, we have one pass, we're going to write to some virtual things. Next pass, we're going to read from these virtual things and output to the actual attachment. And making this work in GL it's not trivial, but it is certainly possible, considering that on desktop we would have to go to a deferred rendering path anyways, where we could say our subpass input attachments now just become regular texture load. And then less, we could do some trickery to rewrite our inputs into pixel local storage blocks and output blocks, that kind of stuff. It gets pretty tedious because it has to change, or it has to go through the shader and figure out which inputs should be PLS, which outputs should be PLS. But it's certainly doable automatically. That way we can support PLS and Vulkan subpass in the same kind of interface. Synchronization was, so in the beginning, what you can do to make your life easy, when you submit something, just do a full stall every time to avoid any kind of synchronization problems. But as soon as you can, try to move away from it, because you can easily fall into a trap where you just can't get away from those full stalls. Because some bug comes up and you have no idea where it happens. As soon as possible, you have to get away from this model and actually overlap stuff and try to do it right. So there are lots of hazard cases you will run into, like using output from previous render pass, you're doing some compute maybe that you will use in a render pass, that kind of stuff. I'm not going to cover much of synchronization since it has been done in great detail today. Yeah, let me just give this a sec. No, I can't. Okay, I'll talk about what we did there. So, there are basically two ways of dealing with synchronization in practice. There's one way where you check all your writes and say, okay, these resources are potentially in flight. You have to be very careful about them. And every time you read that resource, start doing things like, is this invalid? Do I need to synchronize this resource? Every time you find a texture, is this a valid texture? And as you can probably imagine, this gets into GL territory where you have a ton of overhead just doing stupid checking that you shouldn't need in the first place. So we decided against that path. And we went to the model where if you're writing something, you pretty much know what that resource is being used for, right? If I'm doing a render pass, let's say my main graphics pass, you know it's going to be sent to the post-processing stage. I mean, you know that. If you're doing some compute work, you know that it's going to be used maybe in graphics or maybe in fragment data. You know, 99% of the time, I would say that you know this stuff up front. So in your in our interface, we end up doing things like everything that can potentially touch the GPU or touch memory on the GPU, we basically specify up front what's the hazard case here. And the hazard case would be something like, I'm going to use this in the fragment shader later in the texture cache. And we say that up front, and when we do the operation, inject the pipeline barrier. And at that point, we can forget about it. It's safe to read anyways. That turned out to be very practical. And if we add a lot of defaults for the common case, then 90% of the time we don't explicitly write synchronization stuff in the interface. That turned out to work out pretty well. I'm sure if you want to do it really well and start dealing with multiple queues and overlapping that kind of stuff, it gets more complicated. And we haven't really gotten there, but it sounds like a much more practical way of dealing with it than trying to track everything in the engine. Because it gets incredibly difficult to do it right. But why do that when you as the application know exactly what you're doing in front? That's the whole point of Vulkan. You don't want to make your Vulkan engine a GL ship. There's no point in doing that. Right, so here's what I was saying again, is that our render paths, we specify which pipeline stages it's going to be used in, which memory domains. And render paths, we can inject a pipeline barrier, which by default will mean fragment to fragment, and call an attachment write to a shader read, that kind of stuff. So image layer transition is also quite difficult concept for us, at least, because we also need to keep track of what are we doing with the image at any one time. Are we transferring to it? Are we rendering to it? Are we reading to it? So the easy way out to get things running is to just use image layout general, which basically means I don't care about performance there, just give me something that works for every case. That's a practical way of doing it, and it turns out for us at least, we don't really care about image layouts. The only thing where we have to care is percent source, where we want to send it to the presentation engine. And the spec is very clear, we need percent source, but we just do that. But be aware that some implementations, and especially on desktop, will definitely care a lot about how you do these things. So don't think that you can ship something like this, at least not on desktop. I'm sure somewhere will tell you that. Or you can possibly use general, you have to use every color attachment optimal, then transfer source. I'm not the right person to ask about that, but I just know that for us, we don't really care. The only thing is that you have to follow the spec in terms of percent source. So to summarize this, the biggest thing, never allocate or release in runtime. Try to recycle things. Try to make allocators that will recycle things for you. So if you recycle, streaming is not a big issue. I mean, if you just allocate something from your own allocator, you know how it behaves. It might not need to be thread safe because you never allocate your multiple threads. you know best what your engine is doing. That's the whole point. So, but be aware that allocating from the Vulkan device is expensive, and you should try to avoid it. Try to recycle things instead internally. And sure, even if you can do a bunch of draw calls efficiently, it doesn't mean that you should throw away all optimization you did for less, for example. There's no reason why you should do that. Unless it can make other things much faster, of course, but that's something you have to figure out. Multi-threading is way simpler in that it's very easy to just kick off rendering work on threads, and it's so much easier to design for this. And there's no reason why you shouldn't design for this, even if you target GL, because if you have a command buffer abstraction, a GL implementation of a command buffer would essentially just be recording a bunch of function pointers with some arguments, right? But when you actually submit them, you could replay the function calls. So it's still very easy to design for multi-threading and fall back to a single thread path nonetheless. For this particular, so at least we recommend using push constants. Try to design for it, we hope. So the tools do make it much easier to use it in practice, since you can easily reflect stuff in how you create your Python layouts, because that would get very annoying. Multipass, especially on mobile GPUs, is really great, so try to design for it. And the good thing, you don't have to care about specific extensions, as Andrew mentioned. The same code will run on desktop and on mobile, and on mobile it should just be faster and less bandwidth. Desktop guys will still like it because it allows them to schedule things ahead of time better. That's sort of the giveaway. All right. Any questions?
Hey, so I'm curious because obviously you said go port Vulkan, basically redesign for Vulkan and then port back to OpenGL. So what was the motivation for not using pipeline objects directly and going to a cache? I mean, it'll work perfectly fine, but obviously it's not very Vulkan-like to do that. It's more OpenGL-like. So is that just an internal complexity reason? Or?
Yeah, so that kind of thing is really a compromise. Because if we start to deal with that we have to bake pipelines up front, then we have to implement the pipeline objects in GL, which gets very tedious. I'm sure it's doable. So it was just a choice we made that it made things much easier to write code, and it's not like we were CPU bound or anything. So it really depends on what you want to focus on. I'm sure you can take this even further and go full on pipeline objects in your interface, but we found it very practical to just not do that.
Okay, but yeah, that makes sense. It was just a
It's a very practical way to do it. It's very simple. But, yeah.
And then was are you?
Yeah.
Sorry. Oh, just a quick addendum to that. So are you building pipeline objects on your main submit?
So the thing we do is that if we haven't seen a pipeline object before, we can decide, do we kick off that pipeline build to another thread and discard the draw call, or do we stall? So it really depends on what's acceptable. In some cases, it's acceptable to just drop the draw call and just kick off the pipeline object in a different thread and wait, or maybe it pops up a few frames later. Or you have to wait, let's say during initialization when you're drawing some initial static environment map, you have to draw everything. So, but yeah, it really depends what's most important. Ideally, again, you would take these pipelines up front. And you could certainly run your application a few times and record which shader variants are you actually using right after this, and start up, just build up all the pipelines that can possibly be used. And then you never run into that situation. That's really a decision in your engine. What is the most important thing?
I noticed recently Microsoft released a sample memory allocator for DX12 developers. The readme was quite interesting because they said This is so that you can get the performance back that you lost by moving to DX12, because people weren't capable of managing their own memory. It was just such a new thing to be doing. I was just wondering if Khronos can provide something similar to get people started.
Well, to be fair, we never ran into a situation where memory management was suddenly slow, where we found it was just incredibly much better in Vulkan. Because consider updating a uniform buffer. I should have mentioned that, but we have a separate allocate for uniform buffers, which is allocated per thread, per frame, that kind of stuff. When allocation turns into an incrementing not-set pointer, right? That kind of stuff. So,
are you talking the game engine here, or inside the driver? When you say we never had problems with allocation, you talk about the way that you allocate
so
your engine.
me is my team writing the engine. But basically, we didn't run into problems where we were seeing bottlenecks due to memory allocation. That was not a thing.
I think that point was more, it's not how long the memory allocation takes, it was that it was being used badly. So you would get a game with 10,000 textures, and people would be running out of memory and swap.
Oh, yeah.
Because previously the driver was doing all that for them.
Exactly. Yeah, in those scenarios, we're not at the point where we actually exhaust memory, so that's not a problem for us. We actually don't deal with that properly. So if that was like a full production engine, you would need a memory allocator that also deals with paging and resources. But we know that that's not a problem, we don't care. So
Yeah, my comment was just, a lot of people will care. A lot of people
exactly. Yeah, I'm sure someone has been looking into it, but I don't know the specific example.
Thank you.
Hi. Related to the previous questions, is there a way of getting the memory bucket?
Yes. So a device exposes a bunch of heaps, and you can query each heap exactly which types it support and exactly how much memory it is expected to support. So you can design your allocator around that. So.
Okay, but it can change on the fly.
No, that's static.
Okay, so if you swap applications, you will not get a notification?
So if
I know that in direct swap and Windows 10, if you are in the foreground now, you launch the app and you might get 2 GB of memory.
yeah,
But if for some reason you switch to another application, the operating system will notify you that you need to release your memory.
Sorry,
Because it's not.
I can answer that question if you're interested or not. The system guarantees 50% of the GPU memory for the running application. You get 25% more, which you can allocate what you want step. When you reach 95% saturation, the system will stop all other applications sharing GPU memory and forces them to release the allocated physical memory in Windows. As in on Windows, the GPU memory is virtualized. So I'm going to have committed memory for the foreground application, 50% guaranteed, and get a forced memory release for all the applications, but not the foreground application. If it reaches 95%, then the other application must give up GPU resources all. So that's like 50% is guaranteed.
Yeah, I know, but if the user for some reason switch, like Alpha,
Yeah, it changes the foreground application.
Sorry, to
which means your application needs to release a context.
Yeah, but Windows is not really Vulkan.
I know, but there is a way on Vulkan of getting this information, or you need to rely on the Windows API for it? Because I know that.
Yeah, sorry, to clarify, that's just Windows, right? I mean,
Yeah.
particularly on Android, for instance, if you've got like a 1 gig system, I know you tend to get out of memory killed at 200 megs. The heap will show you more than that, but it's basically going to depend on the OS.
Yeah.
So Linux is going to do something again, right? That's just probably going to let you run out of memory in many cases, but it's very dependent on the OS. So yeah.
It's unfortunately on Windows it never changes. Sorry, I just wanted to say that Windows never changes, but based on my experience is the budget is set by the OS, but since the video memory is virtualized, it's going to have the same amount of memory. It's just the backing store behind the memory is going to be different. Just
question?
One more.
Oh,
Hi, bear in mind I've been involved in running too, so I might be asking point to speak. How do we handle things like alignment? How do we handle things on alignment? So we do a great big memory allocation, a sub-allocation and that. How do we handle, you know,
right, when you create a buffer for an image, it will say, I require this alignment with these types. So, it all works out.
Okay, thank you very much.
Especially stepping in last minute. Thank you.